Welcome back everyone. In previous section, we learned about the regioselectivity of elimination reactions. In this section, we will talk about stereochemistry of E2 reactions. The stereochemistry of E2 reactions is controlled by conformational effect. E2 is most favorable when hydrogen and the leaving group are oriented in anti and coplanar positions. So what do I mean by that? So as we know that in elimination reactions, we have a leaving group at alpha carbon. So for example, if this represents my alpha carbon, so I must have a leaving group at alpha carbon. So maybe this is my leaving group. And I would need a bit hydrogen at beta position. So this is my beta carbon. So now I have leaving group at alpha and hydrogen at beta. In E2, the base will attack this hydrogen and the bond will move here and leaving group will leave. So this will happen. Now, if you pay attention to the positions of hydrogen and the leaving group, you will see that they are opposite of each other. So this orientation is known as anti. So they are anti-position. So anti means they are opposite to each other. So that's what the anti-orientation is. Now, what's the meaning of coplanar? Coplanar means that they are in the same plane, so within the same plane. They are not projected out or inwards the plane, so they are present within the same plane. Now both alpha and beta carbons are connected with other elements also with a covalent bond. So let's show those bonds also. So for example, alpha carbon may be connected with A and it's coming towards the viewer, and B is going away from the viewer, and this is because we know due to sp3 hybridization it has a tetrahedral geometry. So similarly, let me correct the geometry. Similarly, beta carbon will also be connected with another element C and D. So now you can see that C, D, A, and B, they are not in the same plane as the leaving group and hydrogen, but hydrogen and leaving group, they are within the same plane, but they are anti. So this position is known as anti and coplanar position. So E2 will only happen when the leaving group and hydrogen are in this orientation. So in this orientation, the base will attack the hydrogen and the bond will move to form a double bond and leaving group will leave, and we will get a product. Now this is important. Now remember, C is projected towards the viewer and A is also projected towards the viewer. So both A and C are coming towards the viewer. So therefore, after hydrogen and leaving group are eliminated, the resulting alkene will have a stereochemistry in which a double bond will form between carbon and carbon. The A will be projected towards the viewer out of the plane, and C will also be projected towards the viewer. At the same time, B will be away from the viewer, as well as D will also be away from the viewer. So this is the stereochemistry, and because it's an alkene, therefore the whole molecule is a flat planar molecule, and this stereochemistry will decide whether the resulting alkene will be a cis alkene or trans alkene, depending on what A, B, C, and D are. So because of this anti and coplanar requirement, one of the stereoisomer will predominate over the other. So depending on the values or A identities of A, B, C, and D, we may either have a E configuration or Z. The stereoselectivity of E2 reactions can be better understood with the help of Newman projections. In case of Newman projections, our starting alkene, let's call this carbon number 1 and that's carbon number 2. So carbon number 1 is this one and carbon 2 is behind this sphere. So carbon number 1 has hydrogen on top. So I'm trying to draw this carbon here. So it has hydrogen on top, and if I look from this side, then the C is bonded to my right side, so it will be C will be here and D will be here. Similarly, the carbon number 2 is behind here, so and the leaving group is at anti position, which we can also call it a staggered position. So leaving group is down here, and A is on the right side, so A is here and B is on the left hand side, so this will be B. So in Newman projection, again the base will attack this proton and leaving group leaves because they are in anti and coplanar. So what will happen is that an alkene will form. So I'm gonna draw the rear one down here so that we understand that there is a carbon behind here. So C is still here and D is here, and A is on this side and B is on this side, and there is a double bond here. So if we look from the top, so if we try to look from the top and I tilt it, then the resulting product will be, so this is my carbon 1 and that's my carbon 2 and double bond in the middle. So in this case, then C will be down here and A will be here and D will be here and B will be here. So this is the top view. So as you can see that because of this the anti and coplanar requirement, one of the stereoisomer will be formed, and that's how the stereoselectivity of E2 reactions is calculated. Let's try to understand the stereoselectivity of E2 reaction with the help of an example. Consider this molecule. So in this molecule, our leaving group is present at this carbon. So therefore, this carbon will be alpha, and that's our leaving group. And the carbon adjacent to the alpha, which is this one, so that will be beta. Okay, so let's remove the proton from this carbon also. So there is only one beta position now, and the proton here, that will be the hydrogen on the beta position. So in this case, if elimination reaction takes place, the leaving group and the proton should be eliminated if we ignore the stereochemistry for now. So we know that these two should be eliminated. So then the product will be a hydrocarbon with a double bond between alpha and beta carbon, so which is here. Now alpha carbon is connected with the tertiary butyl group. Let's connect with tertiary butyl group, and it is connected with a hydrogen, so that will be hydrogen, and beta carbon is connected with a benzene ring and a methyl group. Now the question is, will this be the product or will this be the product? Because these are the two possible outcomes. One is E configuration, the other one is Z. Which one is the correct stereochemical outcome, or are they equally likely? So that's the meaning of stereoselectivity, and I can tell you right now, one of these two products is the correct answer, or is the predominant product, or one of them is the major one. So which one? So that comes from the earlier discussion that the leaving group and hydrogen should be in anti and coplanar position. In order to determine that, we cannot determine in this form. Why? Because leaving group and hydrogen in this structure are not in anti and coplanar position. See, this is the leaving group and the anti and coplanar position is here, and at that position, for now, this position is occupied by a tertiary butyl group, so we cannot really calculate the stereochemistry at this point. So in order to calculate it, first we need to come up with the correct conformation. And how do we find the correct conformation? We just simply rotate the molecule so that the leaving group becomes coplanar and at anti position to the proton. So let's eliminate, let's remove these products for now, and let's first try to come up with the correct orientation. So I have to rotate this by 120 degree to draw the molecule in correct orientation. So let me do that. So I'm gonna leave everything as such on beta carbon, and I'm only gonna rotate the alpha carbon conformation. So the benzene ring stays at its own position. The methyl group also stays there. Hydrogen is within the plane. So now if I rotate this way, now the bromine, which is coming towards us, will go and occupy this position, and the tertiary butyl group goes there, and hydrogen goes in this position. So bromide will go there. The tertiary butyl group will occupy the position which was earlier occupied by the hydrogen, and the hydrogen now will come towards us. And remember, this orientation or this conformation or rotation along the carbon-carbon single bond is allowed. The energy required to do this orientation or this conformation is not that high. So now this is the correct orientation. So in this case, now the proton and the leaving group are in anti and coplanar position. So now a base will attack here, and this bond moves here and leaving group leaves, and this will give us the correct alkene stereo isomer. So the best way is to draw the double bond, and alpha carbon is here, and in alpha carbon, if you look carefully, the tertiary butyl group is going away from us. So therefore I'm just gonna draw it, the tertiary butyl group going away from us, and the hydrogen is coming towards us, and the methyl group here is going away from us at beta position. So this is the beta position. So the methyl group is going away, and the benzene ring is towards us. And remember, this is an alkene, so it's in the same plane. So this is the top view. Well, that's the top side and this is the bottom side. So if we flip it towards us, and so this alkene will look this way. So this is the, I just, instead of having it horizontal, so I just moved it to look the top view. So that's the correct. Now we can calculate whether it's a E or Z. I'm gonna leave that part to you guys, but that's how we calculate the correct orientation or the correct stereochemistry of E2 elimination reaction. As in the case of backside attack of a nucleophile in SN2 reactions, there is an orbital based reason for the requirement of anti and coplanar arrangement of proton and leaving group in E2 reactions. As shown in this diagram, that after the removal of proton by base and the loss of leaving group, as you can see from this orbital diagram picture, the filled carbon hydrogen sigma orbital, this one, after the removal of proton, it results in the alignment of two p orbitals, and this alignment can only take place if the hydrogen and the leaving group are at anti position and they are in coplanar orientation. So after these two p orbitals are aligned, they will result in the sideways overlap to form the pi bond. So therefore the elimination reaction or E2 elimination reaction will only take place when hydrogen and leaving group are in the anti and coplanar orientation. So as we learned in previous slide, that for E2 reaction to take place, the hydrogen or proton and the leaving group must be in anti and coplanar position. If they are not in this position, then a rotation around this carbon-carbon single bond will take place, and that rotation will bring the leaving group and the hydrogen in anti-coplanar position, and it will result in E2, and we will get our uh, specific stereo isomer. In case of cyclic haloalkanes, the rotation around the carbon-carbon single bond is not possible. The reason is because all carbon-carbon bonds are linked together to form the ring. So without breaking the ring, this rotation is not possible. So due to this reason, the E2 reactions in cyclic haloalkanes results in interesting uh, products. For example, if we perform an elimination reaction on cis-1-chloro-2 isopropyl cyclohexane, this would be our alpha carbon, and this means that we have two options of beta carbon, either this one and this one. So of course both of these beta positions do have hydrogen, so we get both uh, products, and we know according to regioselectivity rule that Zaitsev product is the major product, and Zaitsev product is the one in which the alkene is more substituted. So therefore this is the major product because the alkene is more substituted, and that is the obvious answer, and that is the desired product. However, instead of cis isomer, if we start with the trans 1-chloro-2 isopropyl cyclohexane, we only get the Hoffman product. The Zaitsev product is completely missing. We do not get any Zaitsev product, or the more substituted alkene not formed. So why it's so? The answer can be found when we look at the stereochemistry of this reaction. Let's try to understand how the stereochemistry of E2 reactions affect the regioselectivity of cyclohaloalkanes. Consider the elimination reaction in case of cis-1-chloro-2 isopropyl cyclohexane. In this elimination reaction, we do get the normal regioselective outcome, that is the more substituted alkene is the major product. So that's what we expect in any elimination reaction. So let's try to understand the stereochemistry of this reaction. So in order to understand the stereochemistry, we must draw the chair conformation of this cyclohaloalkane. So that's carbon number 1, carbon 2, carbon 3, and so on. So if you look at the chloro group as well as the isopropyl group on carbon number 2, both of them are away from the viewer or behind the ring. So therefore, when we draw the chair conformation, so let me draw the chair conformation first. So this would be the chair conformation. So now because isopropyl group is away or behind the ring, so therefore I will draw the isopropyl group at axial position, and as you can see, chloro is also away, or they are at cis position, so therefore chloro will be here at equatorial position. So that means we have hydrogen at number 1 carbon, which is axial, and we have hydrogen at number 2 carbon here, which is axial. Now we also know that the bulky groups do not prefer the axial position, so therefore in this case there will be a ring chair flip, and it will result in occupation of isopropyl group at equatorial position, and the hydrogen will now be occupied at this axial position. Whenever one chair flips to the other chair, the equatorial and axial positions exchange. So chlorine or chloro group was at equatorial, so now in this case chloro will be at axial and hydrogen will be at equatorial. So in this more stable chair conformation, you will see that the chloro group and the hydrogen here, or the proton, they occupy the anti-coplanar orientation. So now the base can attack here, and this bond moves here and it leaves, and it will result in formation of this as major product. On the other hand, this is less stable chair. In less stable chair, the chloro here does not have any coplanar antiposition on that side. However, so therefore elimination does not take place. So now that's how we can predict that the major product will be more substituted 1. However, in case of trans 1-chloro-2-isopropyl cyclohexane, when we draw the chair conformation and we look at it, the stereochemistry of this elimination reaction, we'll see that there is only one possible orientation in which the proton and the leaving group are in anti and coplanar position, and that one position leads to the formation of only one product as a result. So let's first draw the chair conformation of this trans isomer. So in this case, the isopropyl group is below the ring because it's at this position and it's away from the viewer, so it's below the ring. So we will draw it at axial position, and the chloro group is towards the viewer, so it's above the ring. So in that means that the chloro group is above the ring, or in other words is at axial position. And of course there is a hydrogen at equatorial position and another hydrogen here at equatorial position. So in this case you will see here that the chloro or the leaving group does not have any hydrogen at the anti-coplanar position. So in this case, the anti and coplanar positions are occupied by or is occupied by this isopropyl group. However, if we look at this carbon also have 2 more hydrogens. So in those 2 hydrogen, one of the hydrogen is at axial position, the other hydrogen is equatorial position. So now in this case, this axial hydrogen in fact is in anti and coplanar orientation. So no such anti-coplanar orientation exists on this side. Now let's flip the chair conformation and see what happens when we flip the conformation. And we know that the bulky isopropyl group does not like to be on the axial position. So therefore, when we flip the chair, that would be more stable conformation. So this, of course, is more stable. So in this more stable conformation, hydrogen will occupy the axial and the isopropyl group is at equatorial position, and now the chloro will be at equatorial and hydrogen will be at axial. Now you will see, or you can see here in this conformation, that chloro is in weird arrangement now. This chloro cannot have any coplanar or anti-conformation with any other hydrogen. So no such coplanar arrangement exists with any other hydrogen. So no reaction or no elimination reaction is possible in this orientation. So only possible elimination reaction which can occur is when we have less stable chair conformation, and in this less stable chair conformation there is only one orientation in which the chloro and a proton are in anti and coplanar orientation. So this is the only conformation or only possibility in which an E2 reaction can take place, and when that happens, it results in the formation of Hoffman product, less substituted. So double bond will be formed here. So this will lead, oh, excuse me, base attacks the proton here, and this goes here, and leaving group leaves, and this will result in formation of a double bond here, which is not the Zasev product. So this is the less substituted alkene. So that's how the stereochemistry of elimination reaction in case of cyclohelloalkanes can control the regioselective outcome also. So let's summarize the E1 and E2 mechanisms in case of elimination reactions of haloalkanes. If we have a primary haloalkane, in that case, even reaction will not be possible. The reason is that primary haloalkanes will result in formation of primary carbocations, and we know that primary carbocations are not stable, so therefore even mechanism will not be observed. So in case of primary alkyl halides, the elimination will always take place via E2 mechanism. However, in case of secondary as well as tertiary, if we use weak bases such as water or alcohol, even reaction will be favored or even mechanism will be favored. But if we use a strong base such as hydroxide or alkoxide, then E2 reaction will be favored in both secondary as well as tertiary haloalkanes. As we know that many nucleophiles are also strong bases. As a result, they may cause a nucleophilic substitution reaction, or they may also result in elimination reaction. So therefore, nucleophilic substitution and beta elimination reactions often compete with each other. The ratio of the products formed by these reactions depend on the relative rates of two reactions. So in this section, we will try to understand that under what conditions elimination will be preferred and under what condition nucleophilic substitution reaction will be preferred. In case our haloalkane is a methyl haloalkane, only possible reaction will be SN2. Elimination will not be possible, either E1 or E2, none of those two reactions will be possible. Similarly, SN1 will also not be possible. The reason is that methyl haloalkane will result in formation of a methyl carbocation, which is extremely unstable. So in this case, only possible outcome is the SN2 reaction. If we use a primary haloalkane, the major product will be the SN2 product. That will be the main reaction, and this main reaction will take place in case we use a nucleophile which is a strong nucleophile and a weak base, such as iodide and acetate. But if we use a strong and bulky bases such as tertiary butoxide, then E2 will be the major product. And in case of primary alkyl halide, both SN1 and E1 are not favored. Okay, so what we can generalize is that if we use the primary haloalkane and a strong nucleophile but a weak base, then SN2 will be the major product. But if we use a strong bulky base, then E2 will be the major product. If our haloalkane is secondary, then in case we have a strong nucleophile but a weak base and strong nucleophile, then SN2 mechanism will give us the main product, or this will be the major product. But if we use a strong base such as alkoxide or hydroxide, then the major product will be due to the result of E2 reaction. If we use a weak nucleophile or a weak base such as water, methanol, or ethanol, then either SN1 or E1 reaction will give us the product. If we use a tertiary haloalkane, then E2 will be the main reaction if we use strong base such as hydroxide or alkoxide. But if we use a weak base or a which is a poor nucleophile, then E1 will be the main reaction. If we use a poor nucleophile and a poor base, then SN1 will be the main reaction. In this case, SN2 reactions are not observed because SN2 in case of SN2 reaction, the backside attack is not possible because tertiary carbocations are too much sterically hindered, or there is too much crowding around the tertiary carbon. Earlier in this chapter, we learned that in SN2 reaction, the departure of leaving group is assisted by a nucleophile. So nucleophile attacks here and leaving group leaves. However, in case of SN1, no such assistance is needed. Leaving group leaves by itself without any help from the nucleophile. These two types of reaction can be distinguished by the order of the reaction. In case of SN2, the order of reaction is second order because the rate of reaction depends on both nucleophile as well as on the uh, concentration of haloalkane. However, in case of SN1, the reactions are first order because the rate of reaction only depends on the concentration of haloalkane. Another characteristic feature of SN2 reaction is that it takes place in one step, and SN1 reaction takes place in two steps. So with these characteristic features, we can distinguish SN1 reaction from SN2 reactions. Interestingly, chemists have recognized that there are certain nucleophilic substitution reactions which have kinetic characteristics of first order, that is, they resemble the SN1 substitution reactions because the rate of reaction only depends on the concentration of alkyl halide, but yet they involve two steps. And those two steps involve two successive SN2 reactions. So this is a strange and unique phenomenon in which our overall reaction is SN1, but it takes place in two steps involving two successive SN2 reactions. These kind of reactions are observed in those reactants which contain internal nucleophile, most commonly a sulfur atom or a nitrogen atom. And these internal nucleophiles are often present on uh, the carbon atom which is beta to the leaving group. This neighboring nucleophile participate in the departure of leaving group to give an intermediate which then reacts with an external nucleophile to complete the reaction. These kind of reactions are those reactions are facilitated by a participation by neighboring groups. Mustard gases are one of those compounds that react by participation of a neighboring group. The characteristic structural feature of a mustard gas is a two-carbon chain, as shown here, with a halogen on one end and a sulfur, either a sulfur or a trivalent nitrogen connecting the two carbon chains. So these are the examples of mustard gases. Mustard gases were extensively used in World War I because they are poisonous gases and they have a yellow color. That's why they are known as mustard gas, because the color resembles mustard seeds or mustard oil. And this gas was also at one time manufactured by Iraq. This compound is a vesicant agent, which means that it causes blisters whenever it comes in contact with the moisture and skin. And it also causes blindness, so it's a dangerous gas. The unusual thing about the reactivity of mustard gases is that they are primary halide, and yet they undergo rapid nucleophilic substitution reactions with weak nucleophile. Uh, we learned earlier that primary alkyl halides do not go nucleophilic reaction with weak nucleophile. For primary halides, we do need a stronger nucleophile. But this reaction of a weak nucleophile, such as water, is is uh, uh, is unique. The unique chemistry of this reaction can be understood when we analyze the mechanism of this reaction, and uh, in the mechanism we'll see that participation of this neighboring sulfur atom facilitates the substitution reaction of water. In normal SN1 reactions, the first step is the loss of leaving group, and that step generally is a slow and rate determining step. However, in case of mustard gas, uh, although the nucleophile does not play any role in first step, but it is an internal SN2 reaction. So in this case, the neighboring group or the sulfur attacks the carbon where the leaving group is present, and this attack facilitates the loss of leaving group. So because of the assistance by the neighboring group, this step is much more faster, and this results in formation of a cyclic sulfonium ion. And once this cyclic sulfonium ion is formed, then the second step, in which the weak nucleophile water attacks the carbon and it forms the substituted product. So because of the assistance by the internal neighboring sulfur, the rate determining step becomes quite fast, and then in this rate determining step, nucleophile does not play any role. So therefore, overall kinetics of this reaction is still first order, but still the reaction is much faster even with a weak nucleophile. So that is the unique nucleophilic substitution reaction in case of mustard gases. With that, we conclude chapter number 9. In this chapter, we learn about nucleophilic substitution reactions as well as elimination reactions. In substitution reactions, we learned about SN1 and SN2 type of mechanisms, and in elimination reactions, we learned about E1 and E2 mechanisms. Then we also learned about the regioselectivity as well as the stereoselective outcome of these reactions. If you have any questions, please let me know. Thank you for watching this video. Have a wonderful rest of the day.